Myself, Sanjay Agarwal. Basically, good afternoon. Myself, Sanjay Agarwal. Presently, I am School of Engineering and Technology, and before that, I was a Pro-Vice Chancellor in Chhattisgarh Technical University. So recently joined my parent organization. So I am going to start the topic because time allotted, I think it's 25 to 30 minutes, right? 20 minutes, okay. So the topic that I have chosen, that topic is very vast. So I am breaking this topic into two parts. So I am going to discuss about the hybrid photovoltaic thermal system, right? I am comfortable on this one. This is working. Yeah, or I think I am audible.
Yes, sir, you are.
So basically, as you can see, the topic that I have chosen is hybrid photovoltaic thermal. So we have to understand what is the meaning of basically hybrid photovoltaic thermal. So as name is indicating hybrid. Hybrid means what? Hybrid means just mixing of something, two things, right? So here you can see the first term, that is the photovoltaic. So photovoltaic is what? Photovoltaic is just simply you can understand that when the solar energy incident on solar cell, it converts into electrical energy. That means so if solar energy is converted into electrical energy, that will be called photovoltaic. Then another term is coming thermal. That means you will also get some another energy that is called thermal energy. That means the system in which by which you can get two type of energy. One is electrical energy, another is thermal energy. Then it will be called hybrid photovoltaic thermal system. System is what? If you give some meaningful input and you get some desired output, that is called system. So our aim is what? Our aim is to enhance the electrical efficiency of the any photovoltaic system, right? So as you know, the electrical efficiency of any photovoltaic depends on the different parameter. What are those parameters? First one is what is the solar radiation? That is the most important, and it is denoted in watt per meter square, right? Another parameter is what? It depends on the ambient temperature also. It depends on wind velocity also, right? So as you see the curve of the solar radiation, it goes like this one, from 9 to 5, from 9 to this way. 9 at you can say at 9 a.m. solar radiation is 700 watt per meter square. Then at 10 it is 800 watt per meter square, and at 12 noon it will be, you can say, 900 watt per meter square or 1000 watt per meter square, and then it will again start to decrease. So in the same way, the electrical energy that you will get, it will first it will in the from morning to noon it will increase, and from noon to evening it will decrease. So if you see the photovoltaic cell is so what happens in this? There is some movement of the electrons and holes, right? So what happens as the solar radiation is increasing, at the same time temperature of the solar cell will also increase, right? If solar cell of the temperature of the solar cell is increasing, so net flow of electron will get disturbed. If net flow of electron gets disturbed, that means current is decreasing. If current is decreasing, that means output power is what? Power is nothing, it is a just product of open circuit voltage and short circuit current multiplied by fill factor. So as I am saying, the temperature. So always suppose is saying that electrical efficiency is 18%. So if anybody is putting 18% or 20% electrical efficiency, this efficiency is always at standard test condition. And what are those standard test conditions? Means if solar radiation is 1000 watt per meter square and ambient temperature is 25 degrees centigrade, then you will get the maximum electrical efficiency of the solar cell. Like suppose you are purchasing any car from the market, so he or she says that the average of this particular car is 18 km per liter. But all are those are the standard condition. Means if you are driving this car at the 50 to 70 kilometer per hour, right? Like that. So we have concluded that now suppose in the Delhi climatic condition or the Gwalior climatic condition, during the summer, what is the temperature roughly? It goes up to 43, 44, 45 degrees centigrade. And what about the efficiency that was quoted? It was at 25 degrees centigrade. So in the literature it is available, if 1 degree centigrade of temperature of solar cell is increasing, so there will be decrement in by 0.04% electrical efficiency. Like 25 to 26, that means that 1 degree centigrade temperature is responsible to decrease the 0.04% electrical efficiency. Now in reverse of that, you can understand by any means, if we are able to reduce this 1 degree centigrade or 2 degree centigrade temperature by any means, that means you can increase the electrical efficiency of the solar cell. Am I right? Now, question is how you can enhance this electrical efficiency or how you can reduce the temperature of the solar cell. So for that, what you can do, like suppose this one is a PV module, right? This is a one panel. So just you make a one channel or you can say one duct below the PV module, right? And you force the air with help of some fan or it may be the natural circulation. So what will happen? It is a very simple phenomenon. Heat always transfer from higher temperature to lower temperature, right? Now, because due to this solar radiation, the temperature of the solar cell is increased. Now this ambient air is coming in the contact of the base of the solar cell, right? So this temperature is more in comparison to the ambient temperature. So what will happen? As the air will pass through this base of the solar cell, so whatever the heat associated at the base of the solar cell, it will be transferred to the air, right? So heat is transferred to the air, or what is the meaning of this? That means the temperature of the solar cell is decreased. If temperature of the solar cell is decreased, I am not saying it is decreased by 2 degrees centigrade or 3 degrees centigrade. For just understanding, we are saying that temperature is decreased. So in reverse of that, you can say you are able to enhance the electrical efficiency. Am I right? Now, question is, because you are making a one duct below the solar cell, so what will happen? Like this temperature is T1, ambient temperature, and whatever the temperature you are connecting at the outlet point, that temperature is T2. I am assuming it is a T2. So I am saying this, the temperature T1 is less than T2, or you can say T2 is more than T1. So there is a difference in the temperature. So if there is a difference in the temperature, it means what? Basically it is a thermal energy, right? And that thermal energy is what? It is simply, you must have thought in the physics, Q is equal to mc delta T, right? And what is this mc? M is what? M is nothing, it is a mass flow rate of the air, at which velocity air is coming out. And this C is what? This C is a specific density of the air, and this delta T is difference in the temperature. That means our aim was what? Our aim was to enhance the electrical efficiency of the solar cell or the PV module, right? So for increasing the electrical efficiency, what we did? Just make a one channel, and we are forcing the air, and you are collecting the hot air. So electrical efficiency, or you can say electrical output power, is increased. At the same time, you are getting some thermal energy, right? And this thermal energy can be used for some meaningful purpose. Like suppose there is a big PV array, it is installed on the roof of this particular building. So what you can do, this duct can be integrated to this particular room. So you will get some hot air in this room. So it will be called building integrated photovoltaic thermal system. This is one application. Another application is what? You can integrate this hot air to some dryer. Dryer means suppose you want to dry some medicinal plant, like you want to make some mint powder. Generally अपना घर में हम लोग क्या करते थे पहले? घर में अपने अगर आप सभी ने देखा होगा, पहले बेड शीट पे या उस पे करके पुदीना धनिया ये सुखा दिया करते थे. suppose now you are making a one chamber, right? And you are forcing the hot air in that particular chamber. So what will happen? The moisture will be extracted. Drying means what? Extracting the moisture of that particular content is a drying. So by this means we can say you are getting a enhanced electrical energy, improved electrical energy. At the same time you are getting a thermal energy. So the overall energy you can say, or you can say the overall efficiency of system is increased. So that is called hybrid photovoltaic thermal. I am not going in the PV because time is very less.
5 minutes more.
5 minutes left. Okay. यहाँ पे कुछ और चल रहा है यार. इसको बंद कर देंगे, कोई ऑनलाइन है ऐसे. तो ठीक है, ऐसा करते हैं, इसको प्रेजेंटेशन को नहीं देते हैं, ऐसे इस पर डिस्कस कर लेते हैं. अब देखिए हम लोग जो डिस्कस कर रहे थे कि सपोज इस रूम में नाउ वी आर सिटिंग इन दिस पर्टिकुलर रूम एंड you are using some suppose air conditioner of 1.5 ton AC. So 1.5 ton AC means what? It will consume around 2 units of electrical energy per hour. That means for running a 1.5 ton AC, you are consuming 2 units of electrical energy, and this electrical energy is coming from conventional power plant, or you can say the thermal power plant. So you know, if you are using 1 unit of electrical energy from the thermal power plant, that means you are responsible to emit 2.08 kilogram carbon dioxide emission, right? If you are using 1 unit of, just imagine, if you are using 1 unit of electrical energy, that means you are responsible to emit 2.08 kilogram carbon dioxide emission. And you are simply using 1 ton AC जो हम लोग घर में यूज करते हैं 1.5 ton AC, that means you are using 2 units of electrical energy per hour. That means you are responsible to emit approximately 4 kilogram carbon dioxide emission, right? Now what I wanted to say, that means if this 1.5 ton AC is used from this photovoltaic system, you can save 2.08 kilogram carbon dioxide emission to the environment, right? So our aim was what? To enhance the electrical efficiency. So PV system, just मैं दिखा देता हूँ picture थोड़ी सी.
Yes, Sanjay, do you have some result? मैं आपको वो दिखा देता हूँ.
देखिए इसमें क्या करा था हमने, just there is one channel, right? And just we were forcing the air below the PV module, and you are getting the hot air. Now, as I was saying that you are getting a two type of energy, electrical energy and the thermal energy. So I am saying how much energy you are getting. So it is very difficult to answer. Like suppose I am saying I have a 1,000 rupees and I have a $50, and somebody is asking how much money do you have. So what you will do? Either you will convert rupees into dollar and then remaining dollar will be added, or what you will do? You will convert dollar into rupee and that remaining rupee will be added. Similarly, in this particular case, this is the overall energy, means what? This is a thermal energy. Whatever the thermal energy in form of the hot air or the hot water you are getting, that is a thermal energy. And this electrical energy can be converted into equivalent thermal, which is divided by this eta C power. That is called power plant conversion efficiency factor. So much energy, that energy is called overall thermal energy. Similarly, you can convert into the electrical energy. This is one experiment that I did. Whatever I am saying or speaking, whether it is right or wrong, that experiment was done. Just I took one solar cell from the Center for Electronics Limited, Saibabad, and experiment was done. And here you can see that this one is the outlet point. You can see here, and this is the inlet point. And this small fan was used. That fan is basically taken from the CPU. Then this is the indoor experiment that was done. So I know time ho raha hai.
5 minutes more.
And this is the outdoor experimental that I did. There are 3 PV modules were connected in the series, and I experimented throughout the year. क्योंकि हम कोई भी चीज बोल रहे कि आज जैसे बोले सपोज इनका बोला कि दिस स्टूडेंट इज वेरी इंटेलिजेंट, so today he may be the intelligent, हो सकता है कल बदमाशी करे बोले बहुत खराब लड़का है, लेकिन थ्रू आउट द ईयर एक साल में इनका पूरा एवरेज निकाला जाएगा, जो पोजीशन आएगी तब बोलेंगे हाँ he is intelligent or what. So for that particular system I experimented and that I concluded that whatever I am saying that thermal modeling was done and then thermal modeling was validated with this experiment. Thank you very much.
Thank you, Mr. So I think, because I'm sorry that I
No.
Doesn't look nice. I don't like, somebody speaking and then
Because
just stop him. I don't like personally.
He
What I'm saying is we have,
he was also very strict on timelines.
no, but it doesn't depend upon it. This is not my fault.
No, nothing. Thank you.
Any questions?
Any question, please? If no, then I have some questions.
Yeah, please, sir.
The first thing is that you are using, how you are using this first passage software here? Are you using some, active system, something like that?
Some active system for it was here you can see. This is the PV module. 3 PV modules was connected like mechanically, and below the this PV module there was one duct was made of acrylic sheet, or it can be just I took help from the carpenter. Today एक duct बनाए को experimental purpose के लिए. Here you can see that DC fan was used.
I can understand. Now my point is that for running that blower sort of thing,
That fan.
other fan, you are spending some energy.
Yeah, exactly. Exactly.
So have you done this overall calculation that what is the increase in efficiency
Yeah.
because of using this thing,
Right.
whether you are spending more energy and getting less energy by way of increasing efficiency? What is this thing?
This one. Whatever you were saying, that was the generated energy 287.6 unit, and this unit was used by that particular fan. So net was the net setting was the 234.7 energy.
Okay, good. Then another question is that have you seen that for every increase in temperature, each degree increase in temperature, how is the efficiency effective?
Efficiency is basically, as that is the literature is available and experimentally validated. If 1 degree centigrade temperature is increasing, it is roughly 0.04% electrical efficiency is getting down.
One question from.
Yeah, please.
So why this concept is not being so popular in commercial installation?
Sir, commercial basically, as you can see, that particular, this one, basically. The challenge was during the IIT when I was pursuing the PhD. It was very difficult to make the one channel. Initially, I was thinking that I will make a channel at the time of this basically manufacturing of this PV module. So I contact IIT Mumbai that just I want to experiment this particular purpose. So they said, well, you have to take permission from this, that. Then I contact Center for Electronics Limited, Cyber. The general manager of that CEL was the close friend of my guide. Then he also refused. It is not possible at that particular.
No, I can answer your
It is a
question.
challenge to the industry how it can be done.
I don't know much about India, but at the European level, it has been commercialized because we are also doing the test center, So we got 2 systems that are of large size. We tested for their overall efficiency and then given them the report. So in India, the European level, they are using this thing. They are having this CSP collector, and then at the center, you are having your solar cells. Okay, so that range and that is about 20 meters square overall size. Okay, so they are at the European level, they are using this.
Because why I am asking is, see, for example, there are large farms that solar farms have been power plants, and if there is a gain of 2 or 3% output,
Yeah.
what you are showing, it's a huge revenue gain
Exactly.
for the company.
Exactly.
And 2-3% gain is substantially very high.
सर देखिए इसका एग्जैक्ट मीनिंगफुल आउटपुट कहाँ समझ में आता है कि अभी इस रूम में बैठ के हम बस पीवी के बारे में बात करेंगे समझ में नहीं आएगा. जहाँ पर इलेक्ट्रिसिटी अवेलेबल नहीं है गांव में जाइए या इलेक्ट्रिसिटी है नहीं, उस पीवी से अगर एक फैन चल जाता है, बल्ब होने जाता है, वो जो खुशी देती है वो बहुत बड़ी बात है. वो साथ ही में सिस्टम को लगा के और उसको ड्रायर से जो मैं कह रहा हूँ जो हॉट एयर लेयर है, हॉट एयर से छोटे जैसे मिंट पाउडर को ड्राई करना है और उसके जैसे सैसे आ रहे हैं इसके तो छोटे छोटे पाउच बनाने के लिए कि यार वो मिंट पाउडर का या इसका तुलसी पाउडर को बना के बेचने लगे, तो छोटे छोटे उद्योग भी लगाए जा सकते हैं। तो वहाँ इसकी इम्पोर्टेंस ज्यादा समझ में आती है कि जहाँ पर अभी हम बैठे यहाँ इतना समझ में नहीं आता।
Even another option is you can use as solar water heater also.
Yes,
Water
this
heating
fully can be done with help of the water
with the help of
also.
water also.
My some students are doing this also.
Maybe I think Mr. Zingra is very much interested to have some more discussion with you, so that can be done during the coffee break, something like that.
Right.
Let us move ahead.
Thank you.
I think we have to-
Let's present. I request sir to present the memento.
Thank you. इधर लाइट आ गई, सामने है क्या?
थोड़ा सा आगे आइए।
Thank you, sir.
Wish you all the best. So let me invite the next speaker. I think that is online presentation. Dr. Suraya said, okay. So madam, I remember that you given the presentation yesterday also. Can you hear me?
Are you there?
Hello, madam, can you hear me?
Ma'am, are you there?
Hello, Dr. Suraya? Yeah. So are you ready with your presentation? Okay. So you have to share your presentation. Okay. So you can start. You will get 15 to no, 20, 15 to 20 minutes for your presentation.
Do you see my presentation?
Yeah.
Yes, ma'am. We can.
Okay.
Yeah, please.
Okay. So. You see my mic? I can talk.
Yes, ma'am. You can start.
Okay, thank you so much. So first of all, I want to thank Officer Anurag for this presentation. My name is
Yes, ma'am. Can you wait for 1 minute? Ma'am, wait for 1 minute. Whatever.
तो चालू करना 10 मिनट
Madam, there is little technical problem at our end. So excuse us.
Do you want me to?
Yeah, just 1 or 2 minutes we have to wait.
Oh,
We can start. Yes, ma'am.
can you see my presentation?
Yeah, it's okay. You can start your transmission.
Do you see that?
Yes, ma'am.
Yeah, I see it on screen or behind you, I see it, okay? So, thank you so much for this opportunity to present my work. My work is to find the comprehensive analysis of interface based on my type of electronic University of Riyadh, Saudi Arabia. So, my thing here is to present some background regarding teaching and also the motivation. I will also give an idea about the computational methodology rules. Also, I will present results and discuss them related to structure of electronic, elastic, optical properties, and also thermoelectrics. Some conclusion and maybe more opportunities if I have time to discuss the plans of the future, as it is an active project. So the materials are interface. So why we are interested to the interface? Maybe the question is very important. And what define what make a interface different compared to other materials? They can be semiconductors, metals, and also they can have some disorder. So basically, the introduction about the concept of interface, Edward Zittel. So it is around 1930. So where he was able to find compounds with elements highly positive and electropositive onto metals, and he found that they have special properties, especially the structure were playing important role to tune the properties, physical one and chemical one. Then we have Wilhelm Klein, who find he built a model, an approach, theoretical one, to check if nodes and even certain compounds or elements in the nuclear table can create or build central phases. After that, we started in 16 with different Hamiltonians and approaches theoretical one to go beyond the structure and see and explore the bonding. We found some zinters that are semiconductors, and they were very, very tested. So until now, I think there is Ben and Sabin who Sabin did ELF, which is electronic localized function, to see how the electrons are localized around the transition metals in the zintal compounds. Of course, before there were like works related to defects, and if we can create variants from when we are building a structure. And now the topic is increasing because actually traditional interfaces were mainly diamagnetic. They are brighter in mechanical properties. They can include alkali and alkali earth metals. So metals with p orbitals. Their bonding and non-bonding states are fully occupied and sometimes unoccupied. So we know a lot of things about them. So we started having dealing with them, like especially when they have cross-check compounds. And sometimes, of course, you can find electronic semiconductors or metals. So how we can see the zinc. So I'm here presenting some pictures from former works. You can find them in COT, like clusters here. You can see from the first COT family one. So they can be also evolutionary systems. Now, basically, materials based on antimony SB materials. We have also 2D and 3D. So those materials are energy. I mean, once we change the morphology from 0D to 3D, properties are changing. And actually, we found stable, let's say, technique and really sustainable, I would say, better work techniques to synthesize them. And of course, easy to characterize. Now, actually, in literature review, we have done about the interfaces. We can have sometimes interfaces containing transition metals, like the alkali, one primary alkali transition metals, but it's not zinc family. So they are the most abundant, I mean, synthesized and stable. And actually, they are, we can see them like precursor. Actually, the first materials we have done, and they have shown different properties in applications, technological applications like optoelectronics and thermoelectronics.
Excuse me, ma'am.
Yes.
Due to shortage of time, so you can conclude your sessions within 5 minutes.
Oh, oh my God. Okay. So our simple motivation here is like if we can in the future synthesize different materials and make them used in renewable energies and also flexible electronics, especially we can play with structures. So basically, actually, the publications, the research from Dimension AI survey are expanded and exploded. So I was keynote speaker, so I was expecting to have 30 minutes.
Yes, ma'am. But due to some issues, there is 25 minutes to each one. So,
Oh my God. So yeah. So basically here my objectives as a computational mathematics scientist is to use DFT approach and to calculate electronic, of course before that structures and also electronic properties used hybrid approaches to see the mechanical properties, optical properties. We use the classical DFT. I will pass this section because I know people are most familiar with it now. So DFT is among the case to study materials at electronic level. with different robust approaches to calculate or estimate the band gap and related properties. So here we have and actually the hybrid functional because actually it estimates well the band gap. We use different tools like quantumized ETK and VAS. So quantum ETK for structured, elastic, mechanical properties, electrical or electronic and optical, thermodynamic and thermoelectricity were deduced from VAS. So here are some examples of materials that we have studied. So they are based on potassium and copper and phosphate of course and actinide. These are the properties. So the first step was to find the structures and optimize them. It was stable energetically, even mechanically when we calculate the elastic constants and all the properties related to elastic constants like the bare bondage, shear modulus. So to see their application in mechanical behavior. So then for the best structures, we were able to determine with exact precision compared to the experimental one using the hybrid SE. So the main character was like the band gap is hard, 1.5, 1.6, but they are having flat bands. So those flat bands, we can compare them of course with the crystal state, were able to lead to very exciting thermoelectric properties and of course optoelectronics. So we did optical one like absorption, dielectric constant, reflectivity, transmission, the conductivity, because they are very, very important properties to know how we can use them in the optical transfers. And of course, we calculate everything related to zero frequency because this is also one of the mandatory steps to check the optical electronics, especially when it is coming to the application of LEDs and optical waveguides. Thermodynamics, they are stable. Phonons are stable, as we can see here. Sorry guys, I'm gonna finish. And we have all the thermal conductivity, thermoelectric properties. They don't have high Seebeck coefficient, but they have low thermal conductivity. So they are now very, very well used in thermoelectric applications. I wish I have more time, but actually it's okay. I'm so glad to have this presentation with you. And if there is any questions, I will be happy to.
Thank you, madam, for your presentation. Thanks for sharing the result that you have obtained from your research activities. Sorry once again that we have to stop you because of this time limitation. And now I will ask the audience if there is any question. I think everything is clear, so no question from the audience.
Okay.
So as a token of appreciation, I think the organizer will send you this sort of souvenir, maybe by email or something like that. So once again, thank you so much, madam. Thank you so much.
Thank you so much. Thank you. Thank you, guys. Thank you. Bye bye.
So now the session is closed.
Now the session is closed and now there is poster presentation on first floor.
But most important is that you come here at 4 o'clock because the other session will start at 4 o'clock.
4:40. As per the schedule, it's 4:40.
Yeah, 4:40.
It's past this.
I think in the next session there will be one invited talk and then one plenary talk.